Greetings and welcome. I am Andrew Brannon, and on behalf of Caleb Mattson, Noah Peterson, James Ryan, and Grace Schippers, we are AME Automation Team 11, and this is the critical design review for our gantry crane for Acme manufacturing line. As an initial project synopsis, the purpose was to design and fabricate a proof-of-concept gantry crane prototype to be scaled at 6 foot in full length with stations at 1 foot increments. Additionally, there was a 5-pound load and 30 1/4 inch cable given that were to be used in crane operation. The 4 initial goals were autonomous operation, stopping at the weigh stations in any order inputted by the user, keeping the load swing stable and small, and minimizing the time of operation. Midway through the process, there was a revision due to the distance-based virtual learning. The purpose was changed to designing the prototype only suitable for fabrication due to the inability to actually fabricate in person. The scale remained the same, and the goals changed to demonstrating functionality of the subsystems that would have been integrated together, and simulating operation, showing that the crane is able to, in theory, stop at weigh stations in any user inputted order, keeping the load swing stable and small, and minimizing the time of operation. From the customer requirements given to us by Acme Manufacturing for their assembly line, as well as AME Automation given out to each of the teams by our head company, we were able to create 10 important technical specifications that kind of guided the design the team created. First, the prototype must be scalable up to 300 feet for the full assembly line. It must be able to transport the given 5-pound load suspended from the 30 1/4 inch cable. The swing must never exceed 25 1/4 degrees at any point during travel, and it must come to rest within 2 seconds of stopping at a weigh station, with rest being determined as swinging no more than 0.6 degrees. The crane must stop at a weigh station with 0.1 inch linear accuracy and must dwell at each stop for 3 seconds before continuing on. It must be able to travel between these stations in any order, and the system must also have a user interface where people can input the weigh stations in that order, as well as including overall and tolerance inclusive graphs of swing angle, position, and velocity. The team created specification number 9 in order to quantify the minimization of travel time with the goal of 1 second of travel between adjacent stations. And finally, our parent company gave us the specification that the prototype must cost no more than $725. This was in the initial proposal. Upon the revision, there was an additional allotted sum of money, but this guiding value of $725 helped with most of our design decisions, and thus it was left in specification number 10.
Using these technical specifications, we created the system shown here. We decided on a belt and pulley system with 2 rails holding the weight of the cart. This helps to mitigate tensioning issues. I will be going into detail on the subsystems on subsequent slides, but one thing to note here is the belt placement. This is not one looped belt, as it is cut on either end of these plates. This allows the wire and the weight to swing unimpeded in this center area. It also provides us with a tensioning system for the belt that I will describe later. You can also see that it is wrapped around this extra shaft in here to increase the contact angle between the driver pulley and the belt. We arrived at this design with much deliberation, considering lead screws, a motor-powered cart, and of course, the belt. We had 3 main goals for our linear actuation system. We first wanted to remove the motor from the crane body. This would reduce the weight and vibrations on the system. That removed the cart from consideration. We also wanted to reduce friction on the system. While a ball screw would have fulfilled this, a ball screw was outside of our budget. After designing a tensioning system, we settled on the belt and pulley system as it balances high performance with reasonable cost. This is a closer view of the motor drive system. You can see we have the electronics off to the right with the motor and encoder to the left. This gap here was cut because the rails we purchased were just long enough for our needs, so we decided to maximize our horizontal distance. Again here, this shaft is to force more contact between the belt and driving pulley. The idler system on the other side is very simple. There are two pulleys to raise the belt up over the cart to avoid unwanted interaction. And this also has the extra area cut out. This slide shows a simplified version of the idler assembly, only showing the connection parts. The side panels here interlock with the base plate and are held in place by screws in the bottom. In order to transmit the rotation of the swinging weight, we use two clamp collars to secure the wire. This causes the entire shaft to spin and allows the potentiometer to read the angle. As I mentioned before, the belt will be clamped between the purple and yellow plates. This leaves space in the middle for the weight to swing. It also allows us to release the belt for storage and retension it when we need to test. We utilize these carriage blocks over sleeve bearings and roller bearings due to friction and cost. The sleeve and roller bearings have lower integration times as they interface with the T-slotted rail, but T-slotted rail is very expensive for the length we needed. Due to the carriage block's low friction and low cost, we decided the higher integration time was worth the effort.
As previously mentioned, our system requires a drivetrain to move the crane body linearly to the designated way stations along the path. This image shows some of the major components of the drivetrain, including the gear motor, encoder, and motor controller. After the user inputs the desired path for the crane to travel, the control system creates an RPM profile that is sent to the Arduino microcontroller. This profile is then translated into a PWM signal that is sent to the motor controller and subsequently converted to a voltage that powers the gear motor. The rotation of the gear motor's output shaft is recorded by the encoder and sent as a PWM signal to the Arduino microcontroller. This data can be then converted and corrected to give the current position of the crane's body using a dead reckoning system. Our drivetrain system is defined as the motor controller, gear motor, and encoder within the system's overview. Here's a complete breakdown of the components within the drivetrain system, including the belt, driving pulley, motor, gearbox, motor controller, and encoder. In order to analyze the drivetrain system and make critical decisions on our design, we examined an extreme stress state for the crane. This is defined as our max acceleration for half the crane's farthest path that it can travel. The kinematics of this state are shown here on the left, and the max acceleration was determined by calculating the acceleration that would cause the weight to make the max angle of 25 degrees. This acceleration was calculated to be 4.6 meters per second squared, or 15 feet per second squared. Using this extreme stress state, you can calculate the torque and RPM required from the motor as a function of pulley diameter. Modeling the entire crane body as a 15-pound system, the force required to accelerate this system can be calculated. This force can then be used to calculate the required torque from the motor using the pulley's radius. The max RPM required from the motor can be calculated using the crane's body's max velocity converted into angular velocity. Using this stress state, we were able to look at timing belts that can be used to drive the system. We decided to narrow our search down to GT timing belts because their profile allows for precision placement and reduced backlash. These belts are also readily available and affordable with several different options. Within this, we were able to select GT 2mm timing belts. Using our analysis with the torque and RPM curve, we were able to determine that any pulley with a diameter under 2 inches is within the acceptable range for GT 2mm timing belts. This dot designates the RPM and torque for a pulley with a 2-inch diameter, and this dot designates the RPM of a pulley with a 1/2-inch diameter. In terms of choosing a pulley, we chose to look at pulleys with a Fairlock hub. These pulleys are able to interact with the GT2 timing belt, and they are specifically designed for torque transmission with its cap screw design that couples directly to the output shaft of the gearbox. There are also a wide variety of sizes and designs that can be selected. Within this, we decided to choose the 32-tooth pulley. This pulley has a pitch diameter of 0.8 inches and costs about $21. The pulley was chosen because it is relatively affordable, and it was the largest double-flanged pulley available within that 0.5 to 2 inch range that we defined. These flanges are important as they help to secure the belt on its pulley as it is driven. We then looked at gear motor systems, specifically looking at 3 different vendors. The first was Bainbots, which has an integrated planetary gearbox system and is relatively inexpensive. We also looked at Vex Pro, which also has an integrated gearbox system that mounts directly to the motors, and it has an encoder that incorporates directly into that gearbox. Vex also has a wide variety of high-quality motors and drive systems. The last vendor we looked at was DJI, which has a RoboMaster product line. This line was attractive because it featured brushless motors that have greater durability over motors with brushes, as well as a built-in motor controller and encoder. However, this motor's free RPM was too slow for our system, and the product line was extremely limited in its technical specifications and applications, as it's marketed more as a toy. On the right here, you can see some specific motors within these vendor systems. We decided to go with the Vex motor system because of its intelligent integration with gearboxes, motor controllers, and encoders. It is a reliable system that is used in several different industrial applications, and the technical specifications are well documented, as you can see with the two motor curves shown below. We ended up going with the bag motor because of its efficient performance. With a peak current of 53 amps, the motor operates at a high stall torque of 0.43 Newton meters and a free speed of 13,000 RPM. The components were also readily available and able to be shipped. We then narrowed down our research to a more realistic stress state. We decided that an acceleration of 5 feet per second squared would be an acceptable standard. The table on the left shows that the crane is still able to travel to a single way station in less than a second and to the final way station in 2.2 seconds. This acceleration also only causes a 15.6 degree angle for the hanging weight, which is easier to control. Using this more realistic stress state, we were able to create motor curves based on the vendor's technical information using several different gearing reductions. These gearing reductions also account for 90% efficiency, so their curves are comparable to real-world performance. You can see that going from way station 0 to any of these stations, as long as these points are underneath the red rotor curve, their motor is capable of outputting the appropriate torque and RPM. You can see that 7:1 is the largest gear reduction that can do that. This gearing ratio allows the motor to operate close to its highest RPM and most efficient state for most of the travel paths, while still being able to achieve that max acceleration for each travel length. Looking at further components in the drivetrain system, we decided to pick the Victor motor controller. This integrates well with the bag motor because it is made by the same vendor, Vex. It is also able to obtain PWM signals from the Arduino's digital pins and convert that into a voltage that drives the motor. This is done with pulse widths using the equation shown here to drive the motor clockwise or counterclockwise. We also chose the Versaplanetary integrated encoder from Vex. This mounts directly to the planetary gearbox and has the specifications listed here. The frequency and pulse widths are more than sufficient to achieve the level of sensing required. So now to actual testing. We operated the motor at 10 different power levels between 0 and 100% for 2 seconds. This footage shown is slowed down and played at 20% normal speed. We were able to determine the average RPM for each of these powered levels with the mounted encoder, which was then used to calculate a motor controller equation to power the motor at a specified RPM. You can see some of the data obtained here on the left. This test was run at 80% and the error-corrected data has an average RPM of 1,475. The average RPM from each of these power levels was plotted, and the linear fit was used to create the motor controller equation with a constant multiplied by the percentage of the max pulse width, plus another constant. Here's a more detailed explanation of the drive system and its connections. You can see that the power switch and the 40 amp breaker were added to this system to create an emergency stop and prevent damage to the motor controller.
This portion of the presentation will cover the angular sensor that was chosen by our team for implementation and the validation of that sensor. During the pre-prototyping phase, our team looked at a variety of angular sensors and decided to move forward with a potentiometer type. This included potentiometers used for control, as well as rotary position sensors as seen in the two pictures at the bottom of the slide. Some constraints on the system before we picked our final potentiometer was that it must interface with the microcontroller, that the linearity, resistance, and throw must be such that it meets the required precision. Linearity is how the voltage and angle maintain a linear relationship in the sensor. The resistance refers to the internal resistance, and the throw refers to the angular range measured by the sensor. The power must also not exceed the limitations of our chosen power source, and the rotational torque internal to the device must not cause slack in the load wire. Each of these factors was put up against 5 different potentiometers across the whole spectrum of what was available to us, and were ranked on a 0 to 2 scale based on how well they met our expectations, with 1 being meeting expectations, 0 being below expectations, and 2 being above expectations. Linearity, angular range, power rating, and rotational torque were all determined to be sufficient to meet our boundary conditions, as well as not significant enough to distinguish between any of the devices shown. That left us with cost and resistance to narrow down our sensor. The two on the right, the single turn and the wire wound, both had resistances outside of our desired range. 1 kiloohm, 5 kiloohm, and 10 kiloohms were deemed able to be read by our data processor, but 1 and 10 kiloohms were on the borders of that range. Thus, the devices with 5 kiloohms, shown in green, were the ones we moved forward with. Additionally, we had to take into account a precision calculus. Our chosen Arduino Uno microcontroller has a 10-bit onboard analog-to-digital converter. And with those two remaining options, option 1 and 2 shown in the previous table, we were able to get precisions of 0.26 degrees and 0.33 degrees respectively by dividing the angular throw by the number of discrete data points in the 10-bit converter. There is additionally a 16-bit analog-to-digital breakout board that was considered that would give the precisions of 4 and 5 thousandths of a degree respectively, shown in the second line. And this would put us within the tolerance of our design specifications of 1/10 of an inch, whereas without that 16-bit converter, we would be outside of that design specification. This calculus did not allow us to determine which of the two options was better or preferred, but it did give us some insight and the ability to move forward with that 16-bit analog-to-digital converter, and we did make that purchase. Finally, to make this last selection, we looked at a financial calculus. The slotted shaft potentiometer was cheaper outright, but required couplers that would drive up the cost beyond what the hollow shaft potentiometer was at. And with our limited budget, we decided to move forward with the hollow shaft potentiometer shown below. Moving on to the validation, there were two simple tests that were conducted initially. The first was about how fast we could get the readings from this potentiometer to get to our control system. With the MATLAB software, we were able to get 30 to 45 readings per second, whereas with an Arduino IDE, we were able to get 800 readings per second. Our linear encoder limits us with 250 readings per second, so our goal with the angular sensor was to have a value above 250 in order to make it a non-limiting factor in our control system. So we would move forward with the Arduino IDE software, which gives us 800 readings per second. The second test of functionality range confirmed via MATLAB that the pin is showing a full range of 0 to 5 volts, which is what our input source voltage was to the sensor, over its full 340-degree throw. Additionally, the Arduino IDE code confirmed that the pin is outputting 0 to 1023. Those are all the discrete points we expected over the 340-degree range. Thus, we know that our angular sensor is fully functional as expected. In the data precision test shown here, on the right, we had the angular sensor display a single set angle over a course of 1,000 iterations. The primary angle value is shown in the more dark bold line in the center of the graph, whereas some kind of sensor noise was shown at one discrete point above and below that value. So we determined that this was equal to plus or minus one discrete pin value, which translates to 0.33 degrees in the basic setup, and with the 16-bit breakout board would correspond with 5 thousandths of a degree, per the calculus shown on the previous slides. These tests were not able to be run with the 16-bit breakout board due to procurement issues and time limitations, but that is the calculated error reduction we would have expected to see. Moving on to this final graph, this was just a display of the angle changing over time. The left graph shows a zoomed in area of the final iterations in the right graph, whereas the right graph is just a cumulative summary of the trial. This graph displays the full range of 0 to 5 volts as seen on the y-axis, as well as how the MATLAB code has a little bit sparser points due to the smaller number of readings per second. However, as mentioned before, with the IDE code, we would expect a faster rate and more smooth curves. As well, there's a small deadband shown about 1,300 iterations when it transitions from 5 to 0 volts, but we do not expect that to be an issue as we are only operating in a small plus or minus 25 degrees from the vertical range, which will correspond to about 2 to 3 volts on this graph. In conclusion, we are confident with our choice in angular sensor and the addition of the 16-bit analog to digital breakout board moving forward.
To control the system, we must examine the nonlinear governing equations, shown here as equations 1 and 2. Big M is the mass of the cart, little m is the mass of the load, L is the length of the cord, U is the forcing function, G is the gravitational acceleration, X is linear position, and theta is the swing angle of the load from the vertical. Dots represent derivatives with respect to time. Using these equations for control requires linearization, which assumes a small angle and a small square of angular speed. This means that cosine can be approximated as 1, sine as theta, and a theta dot squared term goes to 0. We can model both the linearized and nonlinear forms in MATLAB with a fourth-order Runge-Kutta method. To verify this model, we can use a condition with known results. The cart is initially at rest, the load and the cart have the same mass, and there is no friction or other forcing. When the load is released from 90 degrees, we see the expected oscillation in the nonlinear response. The swing angle goes from 90 to negative 90 degrees, and the cart goes from its initial position out to the length of the cable, meaning that the load and cart are basically switching positions as expected in this harmonic motion. We see that the linearized form is off, because in this condition the small angle assumption breaks down. In control, we use the input force to control position and angle. Our team uses a hybrid control model. Phase 1 is open loop using a predetermined force until Phase 2, control stabilization, which kicks in at a set distance from the desired stop. The team considered PID control, pole placement, and linear quadratic regulation. PID is not forward-thinking, so the two other methods were considered more heavily. Pole placement handles all the variables equally, and optimizing the poles is somewhat abstract, especially when compared to LQR. Q and R are weights in a cost function, which directly relate to the variables we are controlling. A, B, C, and D correspond to position, linear velocity, angle, and angular velocity, respectively, while E represents the cost of implementing the control force. By selection of optimal Q and R values, the resulting gain matrices were found for the 6 distances of travel. These gains can be used for any path of that distance, whether forward or reverse, and a switch statement can be implemented in the microcontroller to select the proper values. This reduces the complexity of microcontroller calculations, which speeds up processing time.
For our system, we required a microcontroller which would be able to read and send data for the motor controller, potentiometer, and motor encoder. This gave us several requirements for hardware compatibility, including 2 pulse width modulation channels, 2 digital input-output pins, and 3 power supply pins. Through an evaluation of options on the market, the 6 models shown below were determined to be the most reasonable. Each of their capabilities were documented. The only capability that any of our models had trouble achieving was cost, for which we had set a target value of $40. You will notice that the models with higher processing power were also more expensive. We did consider this trade-off between higher cost and higher processing power. However, because of the decision we made to operate with an LQR control regime and our use of a potentiometer instead of an accelerometer or IMU, our microcontroller isn't required to perform any complex computations like integration. For this reason, the lower processing speeds are acceptable, and we are able to go with the option that is within our target price range. For that reason, we selected the Arduino Uno. There were several requirements associated with the user interface. For example, the user had to be able to enter stations in any order for the crane body to travel to. There were also several explicit features required to be provided for the user. These included a real-time data display of swing angle versus time, position versus time, and velocity versus position. After arriving at the final station, the user interface then needed to switch modes and display these same values along the entire path of travel. The functionality of the crane's user interface is demonstrated in the following video. As you can see, the user inputs their desired stations for travel. In order to simulate the physical environment, we also included the option to include sensor noise in the displayed results, thus better modeling a real-time physical system. For this demonstration, we selected the path to be from station 0 to 5 to 4 to 6. This will demonstrate the user interface's performance along a long path, a short path, and demonstrate its capability of moving in the forward and reverse direction. The data used in this interface comes directly from our simulation, thus emulating the results we would expect to see in a physical system. As you can see, data is reported at a rate of about 10 Hz. While our simulation calculates system parameters of angle, position, and speed far more frequently, its data was sampled at the 10 Hz rate in order to reflect the actual sample rate and sampling rate limitations of our sensors and microcontroller. Once the crane has arrived at its final destination, the entire path of travel will be displayed. You'll also notice that here, as it settles at any station, there are some fluctuations around the target value. However, these are very small. The values that you're seeing are the sensor noise that we've included and would expect to see in a real-time physical system. Now you can see the data for the entire path of travel displayed.
The performance of the crane can be shown in the simulation GUI. The travel path is station 5 to station 2, although any order can be chosen. This model incorporates several factors to mimic actual operation. Cart weight comes from CAD model data, and random sensor noise and disturbance forces are toggled on. Additionally, while the dynamics are modeled with a very small time step for accuracy, a delay is implemented between sensor readings to mimic sensor to microcontroller processing speed. The crane motion is calculated and plotted, most notably position and angle versus time. Motor and force data is also plotted. We can see the motor ramping up and ramping down. This removes instantaneous spikes unachievable by the motor in the real world. A large spike, as here, indicates that an external force disturbed the system. The gear motor torque speed curve is also plotted, confirming that this motion is within achievable limits. Comparing actual data to sensor data reveals the impact of sensor noise and delays. Actual data is shown in blue, sensor in pink. The plots on the left zoom in on noise in encoder and potentiometer readings based on those sensor tests. On the right, linear and angular velocity are calculated with a finite difference method between readings. A low-pass filter is used to more closely approximate the real motion. Now an animation displays the crane's motion. Finally, this GUI can be used to test system robustness, for instance, by adjusting control values, choosing pole placement as an alternative method of control, or even varying the load weight.
This shows the original budget for our project with the $725 allotment per our design specifications. As you can see, we spent around $175 on the drive system, $100 on the body and the rail, $200 for the support frame, and $200 for the electronics, bringing a grand total of $685.78, which is well under budget and within our design specifications. After the project revision, this budget here reflects the additional parts purchased for individuals and their testing of their subsystems. This comes out to a grand total of $986.24, which is still under budget given the $300 allocation on top of our original $725.
In summary, we can evaluate the performance of our crane by returning to the specifications outlined earlier. We have shown that our system is within the given budget, and our user interface and simulation demonstrated our crane's capabilities to meet most requirements, even when including effects to model real-world operation. The one violated constraint was specification 9, which was set by the team to quantify minimized travel time. On average, the crane does travel between adjacent stations in under 1 second, but when traveling only one station, the crane takes additional time to settle the load swing before stopping. In trade-off, the settling conditions were ranked more important by the team than travel time. So this violation was deemed acceptable, and the team is satisfied with its crane performance. Thank you, and we look forward to answering your questions.